area under the graph. Okay, 5.2 definite integrals. The term integral is seen more and more. So let me clean up this a little bit, the integral. Now we're gonna see something different. Like we talk about the area in 5.2, 5.1. Um, now the area, but specifically we're gonna look at the net area. And later on we will see the total area and the total area and the net area. Sometimes they are the same, sometimes they are not the same. So it depends on the function that we are dealing with. Then the definite integral, which is the main part of the 5.3, 5.2, sorry, and the notation to represent the definite integral. Everything is based on the Riemann sum or the process that we went over in 5.1. And the big picture is about the size and sum technique, which is the concept or the use of the Riemann sum to approximate the area under the graph. And then later on, we will see the property of the definite integral. Evaluating the definite integral using the limit. This part, I'm taking it away, so don't worry. It's not included in the exam or in your quiz, the last quiz, and also in the homework. It's already taken away. So we just focus on the area, net area, total area, definite integral, notation, and evaluate the definite integral, including the property. Okay, for the definite integral, recall what we did in 5.1. We work on the Riemann sum. We have the function which is a non-negative, right? From point A to point B. Point A is the point x0, the point B is the point xn. As we break it into or make it a partition into the n equals subintervals. And then we pick the point, as we call it, the point of calculation. Either use the left Riemann sum, the right Riemann sum, or the midpoint Riemann sum to find the area or the approximate the area under the curve. We add them all up. Add the function values, as we call the function value for the height of the rectangle, and then multiply by the width, which is a delta x. So when we write in the summation notation, and the general form of the Riemann sum, as you see the x subscript k and the superscript star. So that means depends on the the way that we use to approximate, use the left or the right or the midpoint Riemann sum. Okay, so this is called the general Riemann sum for the function f on the closed interval AB as a summation notation. So as we approximate, the better approximation when you have the greater number of the n. For example, the same graph, okay, the same graph, we approximate from A to B. If we make into two equal subinterval, use either the left Riemann sum, right Riemann sum, you're gonna gain and lose like majority portion. But if you make it into like higher number or greater number of the subinterval, you're gonna gain and lose like not as much as the lower number of the n. So basically, the more n, the better, or the greater, I use the term, the greater n, the better approximation. Oops, it didn't do it for me. Greater n or the higher n, that means the better approximation. Okay. So the ideal case or the ideal situation would be taking the limit for n approaches infinity. So we assume that we break it up into like infinitely many n subintervals. So if you make it n approaches infinity, think about the width which is the delta x is calculated by b minus a divided by n. As n approaches infinity, that means that delta x approaches the value 0, or the size of the width is going to be very, very small. And the area, the width of each rectangle is going to be very, very small or very narrow bar for each one of them. So I'm going to go back to this graph real quick. So it's going to be very tiny bar, very skinny one. So as a delta x approaches 0, approaching not equal to, okay, it's very, very small as we increase the number of the n. So from the general form of the Riemann sum, it can be used the limit notation together with the sum or the summation. So the limit, we take the limit of the summation of the height of the rectangle times the width, or this is the limit of the sum of the areas of the rectangles on the graph. If this limit does exist, this one represents the definite integration. Okay, as you compare the notation, the left and the right, we have seen this notation in 4.9. Okay, the definite integral from point A to point B, integrand f of x and the differential dx. We saw this back in 4.9. I'm going to put the notes. This is 4.9. This is called the definite integral. We saw this term, we heard about this term back then. So this is definite integral. And this definition or this symbol, this notation is the same as the limit as the width approaches 0, technically when n approaches infinity of the Riemann sum. As we make it into very, very small width or the narrow bar, so then the approximation gets closer and closer to the area or the exact area. So we can say the definite integral represents the area under the graph f of x or between f of x and the x-axis. So this is a connection of the definite integral and the limit of the Riemann sum. Okay. And the value a and b, the a is called the lower limit, b is called the upper limit of the integration. What are a and b? A and b are the left and the right end of the interval that we work on, the approximation of the area. Okay, so in summary, the slice and sum technique is the way that we use to find the result or find or approximate the area under the graph. And if you take the limit of the Riemann sum, limit of the Riemann sum as the n approaches infinity or as the delta x approaches 0, so it's gonna be the area under the curve. If we don't take the limit, the Riemann sum is just an approximation. When we take the limit, so the approximation gets closer and closer to the exact area. Okay, so we're gonna transform the notation of the limit of the Riemann sum into the definite integral notation. So you see the limit of the Riemann sum, and we're gonna rewrite it and express it into the definite integral form. So what we have to do, we have to know the function. As a Riemann sum, we need the function, right? We need the interval, the closed interval AB, and um, we take the limit as x as the delta x approaches 0. The delta he means delta x or n approaches infinity. From the formula, the delta x equals b minus a divided by n. If we have this information, we're gonna write in the notation of the definite integral as the integral sign from point A to point B of the function as the integrand with respect to x. The dx is the same as delta x as a differential notation we saw in 4.8, 4.9, I believe, 4.7, sorry, in the last the last section toward to the end of the section toward to the end of the chapter 4. So the definite integral from a to b, the function fx dx, and the integral notation, this symbol is technically from the letter s, which is from the sum. You just stretch the letter S stretching it longer and longer and longer. So that means this is the sum when you take the limit of the sum of the function, which is the height, times the dx, which is the width. So that's the concept behind it. The sum, that becomes the integral sign. The height, which is the function. The width is the dx. So the sum of the height times the width, which is the sum of the area, from what bound to what bound, from point A to point B. And we take the limit because we want the bar or the rectangle to be as smaller width as we can. Okay, so that's the whole point of the definite integral. And it's from the idea of using the Riemann sum of what? Sum of the area. And how do you find the area? Length times width, or the height times the width. What is the height? The height is the function. And what is the width? The width is the delta x or the dx. And what is the bound? A and B, from A to B. So from this example, we identify what is the function. So I'm going to write it as, what is the function? The function is the height, which is 4, minus the superscript, and the subscript will tell you the point of calculation. It could be the left end, the right end, or the midpoint, but basically it's any x value on within the interval. If the bar is very narrow or the interval is very small, it doesn't matter you pick the left end, the right end, or the midpoint, the function gonna be very close. So we're gonna use just the notation x in general, but the square, right? So the function is 4 minus x squared. The delta x is the dx. Okay, we have the height times the width and the sum, that becomes the sum of the area. Take the limit. And what are A and B? A equals -2 and B equals +2. From all of this, the notation as a definite integral becomes the integral sign, or the sum of the area, which is from the function, which is the height, multiplied by the width, which is the dx, from -2 to +2. So this is the answer. Basically, the problem asks you to rewrite from the limit of the Riemann sum into the definite integral. That's it. You don't have to calculate anything. Just change from one form to another form using the concept. And then the second one, could you tell me? Okay, let's I like you to share with me what are A and B. So we're gonna make a list. A is, what is the A for part B? Or you can type in the chat if you like. What are A and B? A is 1 and B is, I believe you're gonna say B is 2. Okay. And the width or the delta x is dx. And what is the function value, which is the height? The function gonna be x multiplied by the natural log of the x. Okay. With all of this, the sum is the integral sign. The sum, see the s that stretches from point A to point B. So from 1 to 2, what is the function? X multiplied by log x. And what is the width? The width is dx. So we're gonna need the integral sign, we need the integrand, we need the differential x. So this is the definite integral for this limit of the Riemann sum.